being recorded.
Sorry, Adam.
Past seminar series that include topics like science in the critical zone observatories, sort of a variety of different themes. The theme we wanted to go with this semester is to explore how we're collecting new data to further our scientific understanding of hydrology and of related processes. So to that end, we've put together a slate of 5 speakers this semester. It's my pleasure to introduce Nandita Basu, our first invited speaker for the semester. She finished her PhD at Purdue University, was a postdoc at the University of Florida, returned to Purdue as a research associate, and has been an assistant professor in the Department of Civil and Environmental Engineering at the University of Iowa since December 2009. We'll keep the accolades brief here. Nandita has 24 peer-reviewed publications that she's an author or co-author on, and more scientific presentations and talks than I could count prior to the introduction today. So she's quite well regarded in the community. And it's my pleasure to introduce Nandita Basu, who will be talking to us today about passive water quality sampling.
Thank you, Adam. I would like to start by thanking you all for being here during a Friday afternoon and thanking Adam for inviting me to give this talk. I would like to talk today about, as the title suggests, passive sampling technologies for monitoring of catchment water quality. I'm trying to move slides forward. Okay. So overall, I'll be talking about the motivation, why passive sampling, talking a little bit about advection and diffusion samplers, and a huge amount of static. Is that Nandita? Moment, let me, if you're on the line and you haven't muted your phone already, could you please mute your phone or press *6? It's better, so I'm going to continue. So as I was saying, and I'll talk towards the end of my talk a little bit about the passive flux meter, which a few of us in different universities, so colleagues at University of Florida, colleagues at Purdue University, and here at Iowa have been working on different aspects of this passive sampling device. My background is of a modeler, and as a modeler, I look at modeling or predicting water quality across spatial and temporal scales in watersheds, from the scale of a single soil pad-on to, say, the scale of the Mississippi Basin. More and more, it's being realized that we need watershed-scale studies to understand the role of natural and anthropogenic factors in determining how water quality in streams and groundwater change as a function of spatial and temporal scale. But in order to do that, you would need data. You would need data at multitude of scales, and most often these studies are limited by the lack of adequate data. As an example, here is the Clear Creek watershed, a place where a lot of us at Iowa are focusing our efforts on. It's about 254 kilometer square area, and as I was saying, trying to bring a pointer in here, yeah. So this is the outlet of the Clear Creek watershed, and we have 2 USGS stations at Oxford and Coralville. It's predominantly an agricultural watershed, and one of the watersheds in which there is significantly more data than a lot of others. So if you look at the figure at the bottom, that indicates, the red dots indicates where the Iowa Flux Center is putting in stream gauges. On top of that, at the 2 green points, we have USGS field gauging stations. If we think about water quality, co-located with the USGS stream gauging stations, we have 2 nitrotax sensors. So nitrotax sensors, a lot of you might know, these are really pricey and very good. They give you high resolution data on nitrate in streams. And they are real-time, continuous, really beautiful, beautiful instruments. And we have 2 of them over here. What you see on the right figure is 15-minute nitrate data at the 2 stations over a period of 2 or 3 months. While this data is really beautiful, the problem that happens when you look at something like this is you look at it and wonder, why do you see the difference in pattern at the 2 stations? And it's a question that's not easy to answer, because when you're looking at, for example, this station at Oxford, what you're seeing here is an integrated measurement over a really large area. And at Coralville, it's an even larger area. So in order to make any sense of this data, you need to understand processes that are happening at a multitude of scales. Of course, there are other studies that look at a single stream reach, or might be looking at farms in different portions of this watershed. But how many of these can you study, and how can you take what you are measuring at these smaller scales to be able to understand processes and patterns that you see at a larger scale? Studies at these smaller scales are often done using ISCO samplers. So ISCO samplers are devices in which you are seeing this on the bottom figure over here. There is a set of bottles, and you would sample the water over time, over a storm event. You would bring back the bottles to the lab, and you would measure concentrations. These are not cheap either, and also you need a person to go put them in the stream and take them back. Again, not trivial if you are thinking of measuring at a large number of points within a particular watershed. Of course, you have the traditional grab sampling, which is what most regulatory and monitoring frameworks are based on, where you go take a grab sample at any stream, and then you have a few grab sample data over the entire year. As you might know, grab sampling has tremendous amount of disadvantages. So just to demonstrate that in this figure, again, what you see over here is nitrotac nitrate data taken over a period of 6 days. And the blue dot that you see over here indicates a grab sample. So depending upon when I go out to take my grab sample, I can sample any of these points in the entire chemograph. And my perception of what's happening in the system becomes completely different depending upon which point I sample. And one sample in 6 days is not a bad data set if you're thinking of the graph sampling world, because in the graph sampling world, often you have one sample every 3-4 months. If you had a better sampling regime, and instead of one sample, let's say you are allowed 6 samples, and those are the 6 samples you get. Even in that case, the chemograph that you create out of these 6 samples is very different than what the actual chemograph would look like. And if you take these 6 data points and you estimate solute load, so nitrate load that's crossing a particular section of the stream, it would be very different than the actual solute load. So what is the solution? On one end of the spectrum, we have nitrotax, which is really beautiful data, but extremely expensive. And on the other, we have grab sampling, which is much, much cheaper, but it doesn't really tell us the correct picture. I wanted to use this to put forward this idea of temporally distributed but spatially integrated measurements. So when you measure something here with a nitrotac sensor, what you're measuring is a sample which is temporally distributed, so you have beautiful, beautiful temporal resolution, as good as you want it. But it is a data set that is integrated spatially over a large area of the watershed. In contrast, you can think about another kind of measurement, which is spatially distributed. So you have all the black dots, and you have somehow figured out a way to get measurements at each of these points, so they are spatially distributed. But instead of being temporally resolved, what you get is this black line over here, which means some kind of mean concentration over the duration of deployment. So this idea of mean concentration means it's a temporally integrated sample. And that what you might need is a mixture of these two kinds of technologies. So a sampling scheme that has spatially distributed and temporally integrated measurements along with temporally distributed versus spatially integrated measurements to get a complete picture of the system. Passive samplers do exactly that. They sit in a stream or a groundwater location and they collect your pollutant over time, and they give you some kind of integrated measurements. Passive samplers have been increasing in popularity since the early 2000s, and you can find a lot of details about different kinds of passive samplers in this review paper. But most of the passive samplers that people have worked on and talk about fall in the domain of diffusion samplers. What a diffusion sampler is a porous disk which is placed in water, and the concentration of your pollutant in the water is greater than the concentration in the disk. Because of this concentration gradient, the pollutant gets transferred from the water to the disk, and thus the disk collects the pollutant over time. After some time you take it out, you measure the concentration that has been collected. What you get in this kind of a sampler is also an averaged concentration, but it is a time-averaged concentration. And this is important, for example, when you want to do exposure assessment. So an aquatic organism is collecting a pollutant too. It's collecting it in its fat tissues. So a diffusion sampler can be a surrogate for that and give you some kind of estimate. It works when there are low variations in concentrations. However, when you're dealing with higher variations in concentrations and when you're dealing with the need of measuring solute fluxes, so you want to measure pollutant fluxes at multiple points in your system, what becomes more important is the advective flow through the sampler. Advection samplers are based on pressure gradient. So pressure gradient between the inlet and the outlet of the sampler leads to the flow of water through the sampler. And the sampler has some kind of sorbent which captures the chemical of interest. What you get in an advection sampler is a flow averaged concentration, and I'll talk more details about this in a bit. The advantage of getting a flow average concentration is if you multiply that by the total flow that's happening in the stream, that gives you an idea of the pollutant load that's crossing a particular section. Passive flux meters were the first passive flux meters started in Florida in the groundwater domain. So what you see here, what it was a permeable, or still is a permeable cartridge that's installed in a screened well. So that's what's shown over here. And within the permeable cartridge, you can have different kinds of sorbents. A common one that's used is granular activated carbon. Before deploying the device in a well, you would sorb alcohol tracers on the sorbent. So when water flows through the device, the alcohol tracers are leached from the device. And by measuring initial and final tracers, you get an estimate of water flux through the device. At the same time, your pollutant of interest is captured on the device. Thus, in one deployment, you get an estimate of both the water flux through the device as well as the contaminant flux through the device. Here are just some pictures of the groundwater flux meters being deployed in the field. This is how the granular activated carbon looks like. Here you see one of those cartridges being cut open and sampled out the field. Here is the sampler again, and here you see Sir Catfield and Mike Annable, our colleagues at Florida, who are installing the device in a field site in a groundwater well. What do we get from the device? What you see over here is data from my work when I was doing my PhD. It is a trichloroethylene plume in Australia. What you get is groundwater flux, which is given by the blue line over here, and trichloroethylene flux, which is given by the pink line over here, and how it varies with depth within a particular well. The beautiful thing about this device is that you can actually figure out using it that there's a clay lens here. So there will be less flow through here, or there's a clay lens here, or there is sandy clay here, so greater flux of both water and the chemical through this layer. So you get a depth resolution using this device. Now, you would then want to put a large number of them across a transect, and that would give you flow through a particular transect in your groundwater system. What you see in the figure on the top is a particular cross-section like this, and you see contours of fluxes through this concentration. So most of the solute or pollutant is coming through this red area across this cross-section. Of course, then you have to deal with answering questions. How many wells do you need? How many wells are enough? What are the levels of uncertainty? And there is work going on to answer each one of these questions. This is just a map of passive flux meters deployed across U.S. This is much older map, so the number of locations have changed since then. Now, what we have talked about, or what has been done mostly so far, is the groundwater flux meter. And the idea that you can have these different cross-sections, different transects across your catchment and measure fluxes across this. So think about a study in which you can have these different transects and you can measure nitrate fluxes across these transects. And then you can have surface water flux meters add these black dots, and you can measure surface fluxes through the system. Using this data set, you can then understand the processes and the fluxes that are happening through this entire watershed. So in order to design something like this, we need to work on the surface water flux meters, and that's research still in progress that I will be sharing with you. The main difference between the groundwater and the surface water flux meter lies in the flow field. In the groundwater system, you are going from a porous media, which is the subsurface, to another porous media, which is the flux meter. In contrast, in a surface water, we are going from an open channel flow system to a porous media flow system. So the complications in that are much more. Also, in a groundwater flux meter, you are in a steady state domain, whereas in a surface water flux meter, it's a transient flow domain. You have a storm coming in and going out. You have concentrations increasing and decreasing, and you would be measuring some average over the time period. So here are images of the first surface water flux meters that were designed in Florida. What you see over here is a porous cylinder, so it's just a metal cylinder, hollow metal cylinder, and there are two ports, 1 and 2, on the surface of the cylinder. So when you place the cylinder in a flow field, there is pressure gradient that's induced between these 2 points. That pressure gradient forces the water to flow through this cartridge. This cartridge again has activated carbon for capturing the pollutant of interest, and also it has activated carbon pre-sorbed by alcohol tracers, and depletion of the alcohol tracers lets you know the water flux. Instead of cylinder, you can also have a hydrofoil shape of the device, and then that would define the pressure difference between the inlet and the outlet. So here is results from a plume test of that device. This is cumulative water discharge, true value versus estimated, and this is cumulative nitrate discharge. And as you see, in the flume, the device worked really well, and you could get a really good estimate. This is testing done in the field. Again, this is cumulative water discharge, and in this case, phosphate discharge. The limitations of this device are that flow was assumed to be steady and concentration was approximately constant. There is another modification of this device that's going on, in which what you see over here is an impermeable center tube and then the sorbent tube. Again, there are these ports, and water flows through the device, goes in through this port and comes out through this port. And so here is how the flow field looks like. Now I'm going to jump ahead and talk a little bit about a version of the sampler that we have been working on at University of Iowa and at Purdue. So one of the things about the sampler is that instead of wanting to measure both water flow and solute flow, that has been the focus of the earlier samplers. Here we are saying we don't care about understanding water flow. We have some other device that's measuring water flow. The objective of this sampler is just to measure flow averaged concentration. What we have over here is a simple cylinder. We have two materials, granular activated carbon, an ion exchange resin, because we are thinking about doing nitrate, and then a sand restrictor. So the granular activated carbon captures alcohol tracers, the ion exchange resin is for nitrate, and the fine sand restrictor was put in for reducing flow through the sampler and also to address clogging issues. So in the figure over here, you see that the sampler is being tested in a flume. So what happens in this sampler is what you see over here is alcohol tracers being depleted from the sampler, and that tracer depletion gives an estimate of the total volume of flow rate through the sampler over a period of deployment. At the same time, you have nitrates being captured on the sampler, and that gives you an estimate of the total mass of nitrate captured. You divide one by the other, you get an estimate of flow averaged concentration through the device. You multiply this flow averaged concentration by the duration of deployment, you get an estimate of solute load over the duration of deployment, in this case, nitrate load. So just bringing you back to that original figure that we started out with, these advection samplers gives you this flow averaged concentration that when multiplied with water flow gives an estimate of solute load. We did a whole bunch of flume experiments at Iowa at different velocities. We had a constant nitrate concentration in these streams, and we measured the velocities in the flume. What you see on the figure here is some of those results. We did a range of flume velocities, and we looked at the blue line is the actual nitrate concentration, and the data points are the estimated nitrate concentration. So you can see that over multiple deployments, the device worked at least in the flume. What about in the field? Well, this summer we've been testing it in the field, and this has been one of the driest summers in Iowa, mostly drought conditions. So we have not been able to do as many measurements as we wanted, but here is the few results we have. What you see in the gray line is the nitrotac measurements, and what you see in these maroon horizontal lines are the flow averaged concentrations measured using the passive flux meter. So you see that except for this one over here, for most of the data, the passive flux meter captures the flow averaged concentration relatively well. What about the next step? So going from here to predicting nitrate load. So what we did here was we took these flow average and we multiplied that by the total volume of flows that were measured independently at these USGS stations. And what you see over here on the x-axis is the measured nitrate load using the nitrotac sensors and the y-axis is the estimated nitrate load using the flux meter. You see we have a fairly good behavior between the two. However, one of the limitations is most of the data you see here at the bottom, and then we have one higher data point, hoping for more storm events and filling up this area over here. But overall, these initial results suggest that this might work. I started out saying that one of the primary benefits of this kind of sampling is that we get a spatial picture. So what you see over here is one deployment where, along with these two locations, we also deployed at these three other locations within the watershed. And these are the flow averaged concentrations that you see over a 7-day deployment period. So this data point represents an average over this area, this represents an average here, and this represents an average here. So now we are going from measuring one location to multiple locations in space. The next step would be to use estimates of flow from the Iowa Flood Center's flow sensors, which are co-located, to get estimates of nitrate loads at these locations. From a science perspective, if you think about knowing the fluxes across so many points in a watershed, that would help us in the development of reactive transport models. And also from a management perspective, it would help tremendously to design best management practices, to define where you would have stronger regulations, because you know not only the integrated value at some regulatory endpoint, but also the hotspots in your domain where, like in this case here, right, where the nitrate is coming from or any other contaminant is coming from. The flux meter can be modified. So what you see over here is just a picture of the deployment in the field. The flux meter can be modified for a large number of different things. One is that we've talked about nitrate, but you can think of any pollutant and you can modify the sorbent to capture that pollutant. You can also measure fluxes in the cold season because you can just go underneath the ice on the river and measure fluxes below that. You can measure sorbed pollutants. I'll talk about that in a bit. And also you can detect trace quantities. I'll talk about that too. So here is a design that's not done, but it's something we've been started to work on. When we deployed the flux meter for the first time, one of the things that became apparent is that it was capturing a significant amount of suspended particulates, which you see in the figure over here. And that was reducing the flow through the device. Well, we modified the design, so that wasn't a problem anymore. But the flux meter was still capturing particulate material. We all know that suspended sediments carry a disproportionately large fraction of the pollutant load because smaller the particle size, greater the surface area for sorption, and stronger the pollutant load. Thus, we can actually get the flux meter to capture these suspended sediments, extract these suspended sediments, and measure not only the dissolved pollutant concentration, but the suspended pollutant concentrations in the stream. We can even optimize the particle size of the sorbents to capture the particles of interest and understand those dynamics using filtration theory. That's one of the modifications that's going to come along in the near future. Another modification that is currently going on at Purdue is using the flux meter for looking at really hot, tough pollutants to look at, like hormones. Hormones are really difficult to detect in streams because they have really low detection limits, and they are a pain to analyze. What our colleagues at Purdue, Steve Sassman to be specific, is doing is developing different kinds of sorbents, so surfactant modified zeolite is an example, for capturing androgens and estrogens. Thus, we can measure them directly in the field, and we can even detect them in locations where it's difficult to measure them because of detection limits. The thing about the flux meter is it captures a huge mass over time, so it can overcome some of the detection limit issues. There's also a design that folks in Florida are working on hypereach zones. So in the hypereach zone, you can have a flux meter that has a bottom port over here, and then you have a top port over here. So the pressure gradient can be used to drive the flow through the flux meter, and in the process, understand hypereach fluxes. So to summarize, we started talking about different kinds of sampling. Temporally integrated sampling, which we are talking about, temporally integrated but spatially distributed sampling, versus spatially integrated and temporally distributed sampling. So the second one, the spatially integrated and temporally distributed, is what happens right now, whereas what we are proposing with the flux meters are these temporally integrated but spatially distributed samples. We also talked about passive sampling versus active sampling. So passive sampling means the sampler is in the field and it's sampling as the water flows through it, versus active sampling means you take them back to the lab and measure them. Further, we talked about advection samplers versus diffusion samplers, and that advection samplers are used primarily for exposure assessment, whereas when we are thinking about TMDL studies, which is the total maximum daily load, so in a regulatory framework, we want to know the solute load that passes through different sections of a watershed. And in that case, advection samplers that measure flow average concentrations have a lot more benefit than diffusion samplers. We talked about several types of passive monitoring tools. The world of passive monitoring started with the groundwater, advective passive monitoring started with groundwater flux meters, but we've been talking about different kinds of surface water flux meters. We talked about hypereach fluxes and flux meters related to that. Suspended sediment flux meter is something a student of mine here is working on. There's also been work done, and I've not talked about it right now, but there's work done on fracture flow flux meters, where when you are in groundwater scenarios where there are lots of fractures in the subsurface, you can use these to understand the location of the fractures. And of course, when you have low detection limits and solutes that are difficult to detect, flux meters are tremendously beneficial in capturing those responses. And finally, I started off talking about catchment scale water quality modeling. I wanted to end with that. The design of an integrated monitoring system where you might have some locations where, to understand the processes, you have nitrotac or ISCO samplers, and then to understand spatial patterns, you might use these flux meters. They would give you information on spatially variable fluxes, which would be used to enhance reactive transport models. They would also be tremendously beneficial in the regulatory domains to say where your hotspots are and where you should focus your effort to minimize downstream pollutant transport. So with that, I would like to thank, again, a huge number of people who have contributed to different parts of this talk. And as I started out saying that this is definitely a work in progress, we've been chugging away at it, different people with different resources at different points in time. With that, I would like to thank you all, and if you have any questions.
Well, this is Adam. Thank you very much, Nandita. And although you can't hear it because everyone's muted, there's applause across the country right now. So I'll do my best to help moderate a question and answer. I think the easiest way, so we're not talking over one another, would be for folks on the line to go ahead and type your questions into that chat box that you should see on, I think, the left-hand side of your screens. And we'll go ahead and work through as many of those as we can. And if you feel like we're not answering your question and you've got to jump in, then unmute yourself, and by all means, yeah, we'd love to have you participate. So, Nandita, we've got a question. What's the cost of one of these samplers?
Right now we are making them in the lab. They come at $10, $20 a piece. Of course, you would have to factor in graduate student time, etc. But I would say they would come to less than $50 a piece.
Okay, great. And as a follow-up, how about the cost of analysis when we're trying to look at, for example, the alcohol that remains on that carbon or the processing of the constituents that you've captured?
So I think when you put in the processing, and I'm trying to remember some costs that were actually made for this groundwater flux meter. I might be not completely correct, but I think it might go up to $100 when you're thinking of that. But right now in the lab, non-commercial, even considering the tracer purchase and things like that, I think it's $50. It's still $50 for me. $50 for me.
Okay.
Because there is not a huge amount of GAG that goes into each sample.
Nandita, I had another question while folks in the audience think. What is the shortest and longest meaningful timescales that you've left the sampler in place to integrate over?
Okay, so this is also a question that also showed up in my chat box. So yes, shortest and longest times. So we've deployed them from between 3 days to 8 or 9 days. So that's been the time period we have deployed them over. The deployment time is a function of the flow rate through your system because you want a certain fraction of the alcohol tracers to be depleted. You don't want all of it to go away. You want some of it to go away, but not all. So it's a function of flow rates, a general understanding of flow rates in your system. You would not want to deploy it for like much longer periods of time, like months, because I think there would be issues of biofouling when you have it over that long a period of time. Our activated carbon does come with, is silver impregnated, so that takes care of some of those issues, but the maximum we've done, I think, is 10 days, and it generally is 6-7 days. So we try to say, well, it's 1 or 2 storm events that we are capturing.
Okay, great. Thank you. And I see John Cox asks, how low of a nitrate concentration can we measure?
Again, I think the answer is that it would be also a function of the flow through the system and the flow outside, but you can go, and we did not deal with this question specifically for nitrate because here we were worried more in the higher domain. But for example, with hormones, concentrations that we've been working with are on the orders of nanograms per liter. And you can get measurable concentration in your device with those values. So my guess would be, we've done it here at our site. I think our nitrate concentration went this year to 0.5 to 1 milligrams per liter, and we captured those numbers relatively well. I've not gone lower than that.
Okay, thank you. Let's see, we've got a question from Bill Simpkins related to the Clear Creek site. Why is there so much short-term variation in nitrate at the downstream site versus the upstream? So I think probably specifically looking at one of the first slides you showed about the Nitritax data.
Bill, so that's one of the questions that I've been thinking of also, and I really don't know the answer to that. This is just this summer's data that we've been looking at, and we've been wondering about the differences. I mean, that's one of the reasons I was using that as a motivation slide to this talk. That is, when you're looking at 2 samples that are integrated over large spatial domains to make reasonable estimates on variations becomes sometimes difficult. So I don't have a good answer to that. It's a question I have myself.
All right. Let's see. I see we've got Francois Bergrand is typing at the moment. And certainly anyone else out still on the line, we'd encourage you to continue sending in questions. We've got a bit more time. We can do a Q&A. Francois asks about testing these samplers at other sites. Looks like maybe one of his own, as they've got Nitrotax data coming in.
We would love to do that. We're trying to figure out different sites in which we could sample across a range of conditions. So the answer to that is absolutely yes. Logistics, of course, have to be worked out about students and things like that, but yes.
I'm going to take a I don't know if you can hear me. This is Francois talking here. Can you hear me?
Yes, I can.
Well, it's really great work. I think it's one of the approaches that needs to be done, and I suspect it will be overly applied very soon. This is very good. We have the equivalent of Nitrotax. We have it's actually from it's an Austrian brand. It's called SCAN, and it gives turbidity, nitrate, and DOC. And also we're measuring CDOM, and so we have lots of parameters that we're measuring on a continuous basis, from which we can actually calculate fluxes and so. We can imagine having comparing this your samplers to not only nitrate or one other, but a multiple amount of pollutants or parameters of interest. So I don't know. I was wondering if you would be willing to consider that. And we also are using things in tidal systems, and I see David has a question about that. So would that work there? So anyway, it's a great work, and I just wanted to offer my help to test that somewhere else, because we got lots of really good stations where we could test this here too, in North Carolina.
That would be great. I mean, I think one of the strengths of the device and one of the things that we are interested in testing is multiple solutes simultaneously, because technically if you have sorbents designed on the solutes, you can use one deployment to measure multiples. And that would be really good to test it with at a place where it's already going on. So I see another question regarding a tidal system. So the issue with the tidal system, the flow directions changing, there is a version of the flux meter that I know of. I don't know if it's specifically for tidal system, but Kirk Hatfield at University of Florida, I've heard them talk about a version of the flux meter which is designed specifically for exploring the flow direction in addition to the magnitude. So right now, the flux meter we mainly use doesn't take into account flow direction, whereas that version can give you that. So I'm guessing that would be more applicable in a tidal system.
Okay. Anyone else out there on the line who's got a question, please do feel free to go ahead and type those in. I had one other question, Nandita. Is for what you use to pack the sensor, I guess the media on the inside, is any of that I guess rechargeable, or is that just so low cost you basically empty it out and start fresh every time?
Technically, Adam, it is rechargeable because it's pretty much a resin or a sorbent, so it's the same thing that you use in your drinking water treatment plants. So same like you could actually reuse a filter by just desorbing the chemical for it. Similarly, you could reuse this by desorbing nitrate or the tracers from it. We've not done that. We've not, just because of time constraints and wanted to get on with it, but it is reusable technically.
Okay, great. Thank you.
I have a last question. This series is about innovative instrumentation. I was wondering if I could just do a very quick advertisement. We put together a system that measures water levels using webcams. So I can just type the website where people can go to if they're interested. I think it's a really interesting way to actually have both manual data and automatic data done in images automatically. So if you think that's appropriate, I will do that. Otherwise, I will not. Meaning type a website.
I think certainly if you'd like to type it in the website into the chat box, you're welcome to. And if you would like to send, maybe you could send me a slide or so.
Okay.
And we could add that to another, either at the beginning or the end of another talk as well. To get
I will.
it out.
Okay, I will. Thank you.
Certainly. Okay. Well, seeing no other questions out there, and a lot of congratulations and well-wishing of Nandita in the chat box here. I think we'll wrap this up for our first installment of the seminar series this fall. I see everyone's joining me in thanking Nandita again for a great first talk in this series. And I just wanted to remind you all that if this is a talk you wanted to share with a colleague, a student, etc., these are being recorded and will be on the Quasi's channel on Cyve, which is sort of a science version of YouTube. And I'm sure that Kayla will be making that link available to everyone as soon as she gets these all processed and uploaded. So let's thank Nandita once again, and let's also thank Kayla at Quasi for all of her hard work in really doing all of the organization of this. So thanks to all, and we'll look forward to seeing you on October 19th for our next seminar.
Thanks, Adam. And one more item I just want to say, in addition to the videos being posted on Skyve, they're also available on Quasi's Cyberseminar page. So if you go to the Quasi website, you can also find these recordings there. So thank you.
Okay.
Thank you all.
Thank you all. Enjoy your Friday afternoon. Thanks for spending an hour with us.
Thank you. Bye. Thanks. Goodbye.